All right, what's going on, everybody? Today we're going to be doing another LeetCode problem. This one's called car fleet, and we'll be solving it in C++. So let's get into the video. So they're in cars going to the same destination along a one-lane road. So imagine we have a one-lane road. We've got in cars driving along. The destination is target miles away. So they're all heading towards this target position. So you're given two integers array position and speed, both of length n, where position I is the position of the ith car and speed I is the speed of the ith car. In miles per hour, yeah, I don't mean, yeah, like that doesn't really matter, but basically, yeah, you're given two arrays, one for the position of the car and one for the speed of the car, and then the indices will correspond to like the same car. So you're given, for each car, you're given just position and speed. And then there's obviously the target position that they're all approaching. So a car can never pass another car ahead of it, but it can catch up to it and drive bumper to bumper at the same speed. So basically, well, let me finish reading this. So the faster car will slow down to match the slower car's speed. The distance between these two cars is ignored. They are assumed to have the same position. So like basically, yeah, so think about a one-lane road, right? You can't go faster than whoever's in front of you, right? And then same applies like all the way down all the cars. So you're basically going to be limited by the car in front of you. So a car fleet is some non-empty set of cars driving at the same position and same speed. So, and that's important. So remember, so a car fleet is some non-empty set of cars driving at the same position and same speed. A single car is also a car fleet, because they're going to want us to return the number of car fleets. That's just going to be like the result. So if a car catches up to a car fleet right at the destination point, it will still be considered as one car fleet. So basically, at the point of the destination, how many fleets of cars are there? So like, basically meaning, so like obviously if all of the cars, like if the first car is going the fastest and then the second car is going the second fastest all the way down the list, like if they were just in decreasing, or if the cars were in increasing speeds, like moving for the road, if that makes any sense, like they would all be in separate fleets. But if you have a car that's going faster behind someone and they kind of get stuck together, that's like, that becomes one fleet. So hopefully that makes sense. But yeah, so basically for this problem, I'm just gonna go straight into the code because the algorithm can be a little bit confusing, admittedly, for this one. But I'm just gonna go straight into the code and then just explain everything I do. I'll add some comments and whatnot. So, but the optimal solution, yeah, first of all, I'll just give a brief overview. So the optimal solution is going to be, we're basically going to want to combine the position and speed. We're going to want to put each car into a vector of pairs, where the pair is the first element's like the position, and then the second element, we're going to use the speed and the position and the target for each car to calculate their arrival times, because that's actually what's the most important. If a car has an arrival time, so if a car is going behind another car and they have an arrival time that is calculated to be less than the arrival time, like sooner than the arrival time of the car in front of them, that can't happen. So that's when we know there's a fleet, right? So hopefully that kind of makes sense. So for the optimal solution, right, we're going to combine position and arrival time into a pair, or into pairs, for all of the cars. And what else do we want to do? So we're going to do that. Also, we're going to sort the cars by position. because I don't think they necessarily come, like the positions aren't sorted, right? So that's not very helpful. We need to have these sorted. And that's going to ultimately limit our time complexity to n log n. But anyways, yeah, so we need to sort the cars by position, and then basically once we have all that, we can write our algorithm to count how many fleets there are going to be. So count up the fleets, and that's pretty much it for the algorithm overview. For time complexity for this, we're going to get, like I was saying, we're pretty much limited by sorting the cars, and the sorting is going to be n log n. We're going to have some other loops, but those are just linear. So, but anyways, and n is going to obviously just be the number of cars there are. So that's like the size of the position vector or the size of the speed vector, same thing. So and then for space, we're going to have a vector of pairs. That's also just going to be, well, space is actually going to be linear, but n is also going to be, how many cars there are. So, so that's pretty much it for the overview of the solution. So let's get into the code. So the first thing we're going to want is that vector of pairs. So it's going to be a vector of pairs of integers and doubles, because remember, we're storing the position, and we need to calculate the arrival time, which could be a double because there's integer division, and they don't want us to like truncate. It never says anything about that. It's more of like a physics problem. I mean, really, you would see this kind of physics problem like the SAT, but you know what I mean. The arrival time could have a decimal in it, so we need to compute that like precisely. So vector pairs of doubles for the cars, and then we'll just call that cars. It's going to be the same size as either the speed or the position vectors. So we can grab the size with the size method. So there's our vector of cars, and we also need, well, actually, let's just go ahead and start converting those positions and speeds into our cars vector. So to do that, we could just do a normal C style for loop. So I equals 0, I is less than speed.size again, and then I plus plus. And then to put the cars, or to put the relevant data into the cars vector, we basically are gonna want to make a new pair. Actually, the first thing we do is calculate the arrival time. So let's do that. So that's going to be a double. We'll just call it arrival time. And the calculation for this is we are going to need to cast these integers to doubles before we do the division, so that it works properly there in C++. So we have a double. So we're going to cast and the formula for calculating time is literally just it's distance traveled over velocity. So how do we get the distance traveled? Well, we have to subtract the position of the car I from the target. So that's how you get the distance traveled, right? Because it has to travel from this position toward the target. So that's the distance traveled, and then you divide it by the velocity, which is going to be speed. They call it speed at index I, and we're casting the numerator and the denominator to doubles. So that's for the arrival time, and now we can go ahead and make a new pair. So to be inserted into our vector. So we'll have a pair of int and double, and we'll just call it new pair. You can be called whatever, new pair. And then to put those relevant values in there, the first one's going to be the position, so position I, and then the arrival time is what we just computed, so throw that in there. And then finally, we already allocated the space for cars up here. We know it's going to be the same size as these vectors, so instead of pushing it back, we can just assign it to the index, and that'll work. So Alternatively, you could just like not declare the space first and then keep pushing them into the cars vector, but I'm just gonna assign them since we already declared the space. So the next thing we're gonna wanna do is then sort that vector of pairs. Now you might be wondering, how in the world does this know to sort it correctly? Well, it's gonna sort it by the first element by default. So that's kind of convenient because we'll put the position in the first element and we'll do sort. And it's going to be cars.begin to get the sort from the first iterator, and then cars.end to sort in increasing order from their position. So position like 1, 2, 3, etc. So we sorted those, and then now finally we can count up the fleets. So to do this, let's first declare a variable for our result. So, and the result is going to be the number of fleets. So maybe actually for better clarity, I usually call the value I return res, but for this problem, it's a little bit busy, so I'll make sure that's named well. So num fleets, that's what we'll be returning. It's going to be 0 to begin with. Actually, it's going to be 1 to begin with, because if we look at the constraints of the problem, n is going to be, which is the number of cars, is going to be at least 1. So there's always going to be at least 1 fleet, so we just say num fleets 1. And then let's go ahead and iterate. So we're basically going to want to iterate backwards in the array. So, and then hopefully that'll make sense once I get into the code within each iteration. So we're going to iterate from the very last. Well, actually, the first thing, even before this, we need to know what like the arrival time is of the very first car that arrives. So like the last car in the array is going to be the first car that arrives. And we need to know at what time does it arrive, because that's going to be the limiting arrival time. So let's call that, it's going to be a double because arrival times are all doubles. So we'll just call this earliest arrival is going to be equal to the last car in the array, so cars.back to get that last element, and then to get the arrival time, remember that's the second value in the pair, so we have to say .second. So that's the earliest arrivals. Okay, so now we already know when the last car arrives, so let's not iterate all the way to the end, but just up to the second to last element. And then we basically want to do that while I is greater than or equal to 0. That way we go all the way to the 0th index, and then just decrementing along the way. So basically the code here is going to be, so we're going to be comparing the arrival time of the car before this iteration. Like, so the car that arrived first is the last one in the array, and then we're going to be comparing that to the current car. Like, imagine if we were at like the first iteration of this loop. So if cars at index I dot second, so we're basically going to see if the arrival time of the next car, of this current car that arrives, if it's projected to arrive earlier than the next car, then that would by definition be the creation of a fleet. So we're basically going to, so how many fleets would there be? It's a little counterintuitive here, because there's going to be more fleets when that doesn't happen, right? So if the arrival time of the car we're currently at is like greater than the earliest arrival time, so like slower than the earliest arrival time, then that means this car is going to arrive like separately. So we can increment the fleets there. So num fleets plus plus, and then what else do we have to do? We have to do something else here. Num fleets plus plus, and then we have to update our earliest arrival time to, let's see, it's going to just be the speed of this current car. And that's pretty much it for the code. So we can, after that, we can return res, or not res, num. It's going to be the number of fleets that we counted up there. So that should be it for the code, barring any bugs that I may have put in there. Let's see if this runs real quick. So undeclared identifier, earliest time, earliest arrival. Okay, let's see. Let's just change that to earliest time. That way we're being consistent here. Yeah, it should be good. Maybe. Yeah, okay, there we go. So now it accepted the test cases, so we can go ahead and submit this to see percentages. So beats 96% for runtime, beats 88% for memory. So I'd say it's a pretty good solution. You know, we're right up there at the top for runtime, so that's good. I think a lot of people do solve this one with a stack and maybe some other data structures. I'm not sure, but anyways, yeah, this is one variation of a solution to this problem. So hopefully it helps you understand the problem more and gives you ideas on how you can solve it yourself. If you enjoyed this video, please leave a thumbs up and subscribe, and I'll see you guys in the next. Peace.